Hey, this is Matt Baxter. The problem I chose for my project is the issue of crosstalk between IC interconnect. This occurs because ICs are fabricated on such a small scale that wires in close proximity exhibit capacitance. This capacitance allows signals to be transmitted between wires erroneously. To understand this behavior, I set up a model that produces a pair of coupled PDEs, and then solve these PDEs under various conditions. I developed this model from the distributed RC line model already discussed in class. Here, a segment of interconnect has some resistance and capacitance per unit length. By repeating these delta x segments and taking the limit as their length goes to 0, we get the following equation, which takes the form of the diffusion equation. So how do we account for coupling capacitance? We might have a situation like this, where two lines of interconnect run parallel to each other. Because this geometry is symmetric along the length of both wires, we can add a new parameter, coupling capacitance per unit length, C sub C. By taking two segments of the distributed RC line model and linking them together with our new parameter, C sub C, we get a model capable of describing crosstalk. Now there are a few assumptions made here, namely, the two wires are identical. For a more general model, R and C for each wire could be different. Because I am merely taking a qualitative approach to the issue of crosstalk, I believe this assumption is an acceptable simplification. To get the equations from this model, we solve KVL and KCL for a segment of both wires. First, let's start with KVL. The voltage at the beginning of a segment is simply the voltage drop across its resistance added to the voltage at the end of a segment. Now we rewrite this equation to take a familiar form. Here we see that taking delta x to 0 will result in the definition of differentiation on the left side. This yields the following. Taking the derivative with respect to x results in the equations on the right, which will be used once we solve KCL. Moving on to KCL, we see that the current entering a segment must be equal to the current leaving the segment on the other side added to the current going into the capacitors. Here again the equations are rewritten so that taking delta x to 0 results in the definition of differentiation on the left side. This is shown in the next set of equations. Now, substituting what was found via KVL, we can get a pair of coupled equations only in terms of voltages. These equations are in terms of the second partial derivative of position. Since I'd like to use a finite difference approximation in terms of time, first I want to solve for the partial derivatives of time. This can be done with simple algebraic manipulation and results in the following equations. In these equations, d1 and d2 represent constants in terms of r, c, and c sub c. This form looks similar to the time-dependent Schrödinger's equation, which can also be represented as a coupled pair of diffusion equations. Since we already solved this in class, I took a similar approach to solving the crosstalk equations. The time derivative was approximated with a forward difference, and the second spatial derivative was approximated with a second-order central difference. With these approximations, the PDEs can be solved numerically. Notice that V beta is always in terms of a half time step, as was the imaginary part of Schrödinger's equation. This allows both equations to be solved iteratively because leapfrogging in this way ensures that all necessary past values are accessible. As an aside, solving the crosstalk equations with an explicit numerical method like the one proposed will necessarily limit the values for R and C that will produce a stable solution for a given delta x and delta t. The Crank-Nicolson method might be a possible implicit alternative. Now that the method of solving the system is developed, let's take a look at what we can find out using MATLAB. For the first demonstration, wires will be initially uncharged, and then only one wire will be driven to a logic high value, with a finite rise time. Here we can see the driven wire, shown in black, pulling up a voltage on the undriven wire, shown in red. If the coupling is strong enough, this could cause transient errors in the undriven wire. circle represents when the driven wire reaches 4 volts, an arbitrarily chosen threshold for a logic high value. This simulation showed a capacitive coupling equal to the normal capacitance. In this case, the threshold is crossed at about 31 time units. What would happen if the opposite transition occurred, where one wire was initially charged and then transitioned to a logic low value? As it turns out, the effects of crosstalk are the same with a simple sign change. Like the first case, it takes 31 time units to reach what is assumed to be steady state, a logic low value of 1 volt. Going back to the initial scenario, now we will see what happens when there is no capacitive coupling and the normal capacitance is twice its previous value. As we can see, the undriven wire stays at 0 volts because there is no coupling. Here again, the threshold is crossed at 31 time units. This can be described as effective capacitance. When one wire is transitioning and the other is steady, the effective capacitance is the sum of C and C sub C. When both are transitioning in the same direction, the effective capacitance is simply C. When both are transitioning in opposite directions, the effective capacitance is C plus 2 times C sub C. The next simulation will show opposite transitions with C equal to C sub C. Here we can see it takes about 46 time units to cross the threshold. Now, if C is 3 times what it used to be and C sub C is 0, the effective capacitance should be the same. This simulation supports this hypothesis because it takes the same amount of time to cross the threshold of 46 time units. What are the limitations of effective capacitance estimation? To find out, let's see what happens when the transitions from the last simulation are slightly staggered. Here the second transition occurs at 20 time units. We can see that it takes about 10 more time units for both lines to reach steady state compared to the last simulation. For the effective capacitance estimation to be accurate, both transitions must occur at about the same time. Since they didn't for this simulation, the response is actually worse than what effective capacitance would predict. Since crosstalk appears to be a transient phenomenon, would it be possible to alleviate its effects with a slower rise time? This next simulation shows a rise time of 40 time units. Besides the added delay that could be expected, the crosstalk is about the same with a peak at 1 volt. Unfortunately, slower rise times do not appear to alleviate crosstalk. Perhaps an extremely slow rise time could limit crosstalk, but this would sacrifice the speed of the driven line considerably. Now consider the following. Instead of wires being parallel, what if the wires cross perpendicularly? In this case, only a portion of the wire will be capacitively coupled. For the sake of demonstration, let's let C sub C equal 5 times C. Let's also set the crossover to be near the driving end of both lines. Here, the coupling occurs between positions 0 and 2. The effects of coupling are minimal. The delay in the driven line was hardly increased, and only a small voltage was seen on the undriven line. Now let's set the crossover to be near the load ends of both lines. Here the coupling occurs between positions 8 and 10. The driven line takes much longer to reach the threshold, and the transient voltage on the undriven line is larger and lasts longer. So what's going on here? When the crossover was near the driving end, the voltage could easily be dissipated by the undriven line. When the crossover was near the load end, the voltage had to dissipate through the entire length of the undriven line to reach ground. This lingering voltage increased the effective capacitance for the driven line, making it take longer to reach the threshold. This could be a useful design rule to limit crosstalk. If at all possible, arrange interconnects such that the coupling occurs only near the driving ends. That way the crosstalk can easily be dissipated by the ground plane. The crosstalk that was demonstrated in MATLAB can be dangerous in ICs. For lines being driven, crosstalk increases their delay, and for stationary lines, crosstalk can introduce transient errors. In dynamic logic, this could cause the state of a node to flip, causing a permanent error. To ensure performance and reliability of an IC design, this detrimental phenomenon must be minimized. With modern IC design, it is often difficult to find routings for interconnect that minimize crosstalk while navigating design trade-offs. By gaining an intuition of the behavior of crosstalk, it may be possible to develop more nuanced solutions to this problem that better adhere to the established trade-offs. These solutions give IC designers more tools for refining the speed and reliability of their products. The goal of my analysis of crosstalk was to gain such an intuition. Because of this, I avoided using real-world parameters. However, for a complete quantitative analysis, these parameters could easily be included. Thanks for watching.